Welcome to AI Paper Slop. We're skipping the usual banter today because we need to tear straight into a paper that completely rethinks how we handle GPU memory bottlenecks.
Yeah, we're diving right in.
The paper is called FlashMemory-DeepSeek-V4, Lightning Index Ultra-Long Context via Lookahead Sparse Attention. It's from researchers at Tencent AI Lab, HKUAT, and Tsinghua University.
It's a massive deal for anyone working with long context.
Right. So here's the absolute bottom line for you if you were deploying models today. They built a novel inference paradigm called Lookahead Sparse Attention, or LSA.
And LSA basically proactively predicts and fetches only the critical key-value cache chunks that are actually needed for generation.
Exactly. And by doing this, it cuts the average physical KV cache footprint down to a mere 13.5%.
Which is, an 86.5% reduction in memory overhead.
It's insane. And it does this while actually increasing accuracy by 0.6% across major long context benchmarks like LongBench-v2, LongBench-v2 and RULER.
Yeah, you get better performance for a fraction of the memory.
Crucially, they achieved this using what they call a backbone-free decoupled training strategy, meaning they trained this memory indexer on a single H20 GPU in just 1 hour.
Unheard of efficiency.
Right. But there's a fascinating meta detail here. Despite all these breakthroughs, the project is currently suspended due to organizational realignments at Tencent.
Yeah, so what we're dissecting today is basically a highly successful, fully transparent postmortem of an engineering marvel.
Which is incredibly rare to see. So let's set the stage. This paper attacks the single most brutal dilemma facing any ML engineer right now.
The memory wall.
Exactly. You want infinite context windows, right? You want your model to ingest 1 million tokens to analyze a massive code base or, an entire library of documents.
But the linear scaling of the KV cache footprint acts as this hard mathematical wall. You simply run out of GPU RAM.
Current foundation models do try to mitigate this. Like if you look at DeepSeek-V4 or Quinn 3.5.
Yeah, they use heavily compressed attention, or HCA, alongside linear attention layers.
Right. DeepSeek famously has that massive 128-to-1 compression ratio, so they are already trying to shrink the footprint.
Yeah, but mitigation is the key word there. It's not a cure.
Right.
Because to preserve fine-grained factual recall, architectures that use HCA still have to retain a significant number of uncompressed or full attention layers.
So memory is still growing.
Exactly. The slope of your memory growth graph is less steep, but it's fundamentally still scaling linearly alongside your sequence length. So eventually your sequence length outpaces your hardware.
So the researchers dug into real-world inference logs to figure out what was actually happening during these massive context generations. And they found a glaring inefficiency.
A massive waste of resources, really.
Yeah. They found that over 90% of user requests with contexts longer than 64K tokens can be accurately resolved using only the most recent 8K tokens.
Which means conventional LLMs are effectively squandering massive amounts of GPU memory on inactive context that contributes, absolutely zero signal to the current decoding step.
It's just sitting there.
Right. The model computes and holds the entire historical KV cache in active memory out of pure obligation to the architecture.
It's like carrying an entire university library in your backpack everywhere you go, just in case you need to reference a specific footnote from one single 19th century encyclopedia.
That's a great way to put it. It's exhausting and wastes all your energy.
But, if I'm an ML engineer looking at that 90% statistic, my first instinct is to just take the easy way out.
The sliding window.
Yeah. If 90% of the time I only need the last 8K tokens, why not just use a standard sliding window attention? Just discard the history beyond 8K, lock the memory usage, and be done with it.
Right. But there's a huge catch. Implementing a strict sliding window completely breaks the model for the remaining 10% of tasks. And that 10% represents the complex workloads people actually want long context models for. Tasks requiring deep global context synthesis.
Like document-wide reasoning or multi-hop question answering across a massive code base.
Exactly. If you discard the history, the model basically develops amnesia and fails entirely on those tasks. The goal here is to support deep global reasoning without paying the full GPU memory tax for every single local generation step.
Which leads us to the actual mechanism they built, Lookahead Sparse Attention.
Yeah, LSA.
Because passive memory retention is just economically unviable, LSA proactively predicts future context demands.
Right, so instead of sitting passively on a mountain of data, LSA uses a neural memory indexer.
And this triggers periodically during decoding, right?
Exactly. Specifically, every tau equals 64 decoding steps. It evaluates the current hidden states of the query token and looks ahead to predict which historical compressed sparse attention chunks, or CSA chunks, will be needed.
For the upcoming generation phase.
Right, and then it fetches only those critical chunks from a cold CPU pool into the active GPU memory.
So they are dynamically paging memory in and out based on semantic necessity, not just recency. But to make this work, they had to gut DeepSeek-V4's native lightning indexer.
Yeah, they had to completely rip it out.
Because the native architecture uses a rigid top case selector, and LSA replaces that with a Sigmoid activation function.
Right, which outputs a normalized score between 0 and 1.
And it dynamically recalls any chunk with a score of 0.5 or higher. But why is moving away from a fixed top K to a 0.5 threshold such a big deal?
Well, think about it. A rigid top K selector forces the model to recall a fixed quota of entries, completely regardless of their actual relevance.
Oh, I see.
Imagine setting K to 50. If you ask a question where only 2 chunks of historical context actually matter, the top K indexer is forced to blindly pull in 48 additional chunks of pure noise just to hit its quota.
And that low probability noise severely pollutes the attention mechanism.
Exactly. The dynamic sigmoid threshold acts as an expert attention denoiser. If 0 chunks cross the 0.5 threshold, it pulls 0. If 50 cross it, it pulls 50.
It perfectly isolates the signal.
Yeah.
That makes total sense architecturally, but it introduces an immediate bottleneck with the training data.
The golden labels.
Right. Because if you're going to train a neural network to act as this highly calibrated 0.5 threshold gatekeeper, you need incredibly clean golden labels to teach it what a relevant chunk actually looks like.
And naively taking the union of all top K entries creates massive label inflation.
Yeah, the paper mentions it generates almost 10,000 positive samples per token window. It's just an unmanageable ocean of false positives.
So to fix this, they engineered an offline denoising pipeline run over a frozen DeepSeek-V4 flash backbone.
And the mechanics of this denoising pipeline are brilliant because they didn't rely on human annotation at all. It's a 3-step process utilizing cross-layer majority voting.
Right.
So step 1 is softmax normalization. Why did they have to start there?
Because the raw logit scores coming from the 21 compressed sparse attention layers are totally uncalibrated.
Okay.
Applying a standard softmax over all historical entries converts those raw scores into a valid, mathematically sound probability distribution. You have to normalize the outputs before you can compare them.
Makes sense. Once normalized, they move to step 2, which is top thresholding, with a nucleus threshold of p equals 0.6. This feels very deliberate compared to just taking the top 10 scores.
It is. Top-rip, or nucleus sampling, retains only the high-confidence entries that cumulatively make up the top 60% of the probability mass for that specific layer.
So it dynamically shears off the long tail of irrelevant noise.
Exactly. Some layers might hit 60% probability mass with just 2 chunks. Others might need 20.
Which sets up the final filter, step 3, cross-layer majority voting. This is where they demand consensus.
Right. An entry is only officially marked as a golden label if it secures independent backing from at least theta equals 3 layers out of the 21.
So single-layer spiking might just be a hallucination.
Yeah, or an artifact of syntax. By requiring structural agreement across multiple layers, they guarantee the chunk is fundamentally necessary.
And running that 3-step pipeline distilled the noise down to a pristine training set of about 10,000 long documents, ranging from 16K to 512K tokens.
Which is exactly what unlocked the most radical engineering feat in the paper, the backbone-free decoupled training strategy.
Yeah, because fine-tuning a massive large language model on 500,000 token contexts is traditionally a computational nightmare.
Usually requires clusters of top-tier GPUs running for weeks.
But they bypass that entirely. Because the Golder labels and the historical compressed indexer keys were pre-computed and frozen, they physically isolated the indexer training from the massive LLM backbone.
Right. The billion-parameter reasoning backbone never even enters the GPU memory during this training loop.
I picture this like training an executive assistant to recognize which files to pull from the archives, without forcing the assistant to actually sit down and memorize the contents of the files themselves.
That's a perfect analogy. They formulated the whole thing as a standard dual encoder retrieval architecture.
So what were they actually optimizing?
They only optimized the low-rank query projection matrices using a binary cross-entropy loss, or BCE, just teaching a lightweight module how to map the current query state to the frozen historical keys.
And if you're listening to this, the efficiency win here is just staggering. Because they decoupled it, they trained this memory indexer on a single H20 GPU in just 1 hour.
It's wild. And because it was so cheap, they executed roughly 500 distinct training runs in a week.
Which allow them to hyper-optimize the architecture. Let's talk about the results of those 500 runs, starting with routing and placement. You can't just slap a memory indexer on every single layer, right?
No, that defeats the purpose of saving compute. They found that placing indexers on early, shallow layers failed completely.
Why is that?
Early transformer layers are too focused on low-level token statistics, grammar and syntax. They lack the global semantic awareness to predict long-range dependencies.
Okay, so what about scaling up? They tried an 8-layer joint configuration, right?
Yeah, but the indexer became far too greedy. It fetched up to 49% of the historical chunks.
Which puts you right back in the territory of burning through GPU memory.
Exactly. The sweet spot they found was exactly 3 intermediate layers, layers 10, 12, and 20.
And they used OR-ARM mode routing for those, meaning if layer 10, 12, or R20 scores a historical chunk at 0.5 or higher, it gets fetched.
It acts as a highly robust safety net.
But dialing in the accuracy of those 3 specific layers required some specific training recipes, like query low-rank conditioning.
Right. They increased the internal low-rank projection dimension, the R value, to 2048.
Which is not just a simple LoRa fine-tune adapter.
No, they natively expanded the spatial projection capacity of the Lookahead indexer. It needed the representational power to handle complex spatial mappings across hundreds of thousands of tokens.
And the second major recipe was replacing standard BCE with a sample-weighted focal loss, setting gamma to 2, combined with a 3-to-1 negative sampling ratio.
Right.
Now, focal loss is typically used in object detection to handle class imbalance. How does it apply to reading 500,000 tokens?
Well, when you scan that many tokens, the vast majority of chunks are obvious negatives. They're totally irrelevant. If you use standard BCE, the optimizer gets overwhelmed by the sheer volume of easy negatives and stops learning the subtle differences.
So focal loss fixes that.
Yeah. With gamma equals 2, the mathematical penalty for getting easy samples right is drastically downweighted. This forces the optimizer to focus intensely on the hard boundary tokens, the ones ambiguously close to that 0.5 threshold.
And pairing that with a 3-to-1 negative to positive sampling ratio cleanly handles the extreme class imbalance, without forcing engineers to guess at finicky class balancing coefficients.
Exactly.
So out of those 500 runs, what didn't work? What degraded performance?
A few things. Moving from point-wise calibration to pairwise ranking yielded no gains.
Interesting.
And surprisingly, hard negative mining, like using LLM-annotated semantic chunks to try and trick the indexer, it actually introduced severe secondary label noise that hurt accuracy.
Oh, wow. So trying to be too clever backfired.
Yeah, weighted loss functions based on native layer matching counts also hurt the absolute recall bound. In the end, simplicity and strict point-wise optimization won out.
Okay, so how does this highly optimized 3-layer indexer actually perform? They benchmarked flash memory against the standard DeepSeek-V4 flash baseline, a recency-only sliding window, and a random 10% routing control.
And the numbers are striking. Across LongBench-v2, LongMeval, and RULER, flash memory drops the GPU memory footprint to 13.5%.
There's that 86.5% reduction again.
Yeah, and yet it pushes average accuracy up to 77.5%. That's a plus 0.6% improvement over the full context baseline.
So slashing the physical memory by nearly 90% actually resulted in higher accuracy.
Because it acts as an expert denoiser. By throwing away 90% of the context, it removes thousands of irrelevant chunks that would otherwise clutter the attention dot products.
And at extreme 500K scales, like on LongBench-v2L, the footprint drops by a full 90%, yet accuracy beats the baseline by 1.9%.
And we know the indexer is doing intelligent predictive routing because the recency-only and random 10% baselines completely collapse under those same memory restrictions.
Right, they fail entirely to synthesize global context. It's not getting lucky.
Exactly.
But in the spirit of transparency, we have to talk about the limitations. As we mentioned, this is a post-mortem because the project is suspended.
Yeah, though organizations can reach out to yanwang.brandon@gmail.com for compute sponsorship or scaling tests.
Right. But the authors transparently break down 3 major failure cases where this entire paradigm breaks. Failure case 1, context-independent overhead.
So theoretically, if you give the model a task requiring 0 historical context, like translating a single sentence, The Sigmoid gator should output zeros across the board.
Keeping the KV cache overhead strictly constant.
Right. But tested on adversarial no-context tasks, the pointwise Sigmoid gating leaks a marginal background probability.
And as you scale from 125K to 500K tokens, those false positive retrievals inflate the absolute chunk retention volume by 2.5 times. It fails to keep that strict constant memory floor.
Then there's failure case 2, dense global memory breakdown. On the multi-range context retrieval benchmark, or MRCR, accuracy absolutely plummets from 76% down to 48%.
Even when they ran an Oracle simulation and handed the indexer 50% of the mathematically perfect golden chunks, it still failed. Why?
It's the decoupled training. Because they froze the key representations to speed up training, the indexer operates purely via a coarse static dot product similarity. It fundamentally lacks multi-turn late interaction.
Like Colbert-style cross-matching.
Exactly. Colbert keeps token-level embeddings, so every token in the query calculates a similarity score against every token in the document. LSA uses shallow dot products.
So when a benchmark needs to synthesize dense dependencies scattered across dozens of points in a 500K context, a static dot product just can't resolve it.
Yeah, but adding Colbert-style cross-matching would instantly destroy that 1-hour training efficiency.
It's a brutal trade-off. Which brings us to failure case 3, the length generalization ceiling.
Right. The team assumed that because pointwise matching shouldn't theoretically care about pool size, they could train on a 128K and zero-shot scale to 1 million+ tokens.
But that shattered in practice.
Yeah, the indexer strictly hits a ceiling at 2 times its training context length.
It's like having a map coordinate system that suddenly just runs out of numbers. The model was trained up to 512K tokens. But beyond that, out-of-distribution positional embeddings cause block selection to completely degenerate into near-random sampling.
Because it was trained entirely decoupled from the main backbone, it never learned how to interpret positions mathematically beyond what it saw in that 1-hour training run.
It really highlights the gap between text retrieval systems and self-attention mechanisms when it comes to positions. But stepping back, we're looking at a suspended project that proved you can slash memory footprints by 86.5% while boosting accuracy simply by decoupling the indexer training.
It's a massive proof of concept.
It really is. And I want to leave you listening at home with a final provocative thought. If we can successfully isolate the memory indexer from the reasoning backbone to this extreme degree, are we moving toward a future where large language models function purely as stateless compute engines?
Like a CPU.
Exactly. While entirely distinct, highly optimized neural retrieval modules act as the RAM, it feels like this decoupled architecture could eventually completely destroy the concept of fixed context windows altogether.
You no longer have to retrain your billion-parameter compute engine just because you want to read a longer book. You simply hot-swap your retrieval RAM.
Think about how you might apply this backbone-free training to your own retrieval or context scaling bottlenecks. We might soon see massive models running million-token contexts natively off consumer hardware, all because we finally learned how to open only the exact pages we need.